뭔가 이상한데? 전보다 근데 누가 이렇게 해놓고 갔을까? 네. 자, 여러분 혹시 질문하실 거 있으면 지금 편하게 질문해 주셔도 되고요. 오늘 시간은 5분 남았습니다만 자, 먼저 오신 분들 체크 한번 해볼까요? 이재혁 씨,
네.
네. 고하늘 씨,
네.
네. 심준호 씨,
예.
네. 이승진 씨,
네.
네. 이정태 씨, 이충아 씨, 네. 정상아 씨, 홍주표 씨, 김민선 씨, 김유신 씨, 네. 배민열 씨, 배서령 씨, 서하연 씨, 그다음에 조대현 씨, 네, 대현 씨, 최승규 씨, 김성순 씨, 미스터 마이클. Okay, I check the attendance once again. 이정태 씨 오셨나요? 정상아 씨? 홍주표 씨. 김민선 씨. 아직 안 오셨고. 배민열 씨? 네, 배민열 씨. 배서령 씨? 네. 그리고 최승규 씨. 최승규 씨 아직 안 오셨고. 김성수 씨. 네, 알겠습니다. Okay, it's 9 o'clock now, so I will check the final call for your attendance. 정상아 씨? 정상아 씨 아직 안 오셨어요? 김민선 씨? 아직 안 오셨어요? 그리고 최승규 씨? 네. 네, 최승규 씨. 그리고 김성수 씨. 오케이. 누구시죠? 김성수. 네. So this is lecture 22, and I have found that unfortunately we have not many remaining lectures due to the National Election Day and also Memorial Day. So we will have only 4 remaining lectures starting from lecture 22, and it will end at lecture 25th. So if there is something we have to cover, if it remains, then I will try to make a video for you. So please watch those videos. But I hope that maybe we can live without those makeup videos. So another notice is another thing is our TA. is Mr. Kwang Lee, and he is really diligent, and he gave me his own feedback on your homework. So he's found that nowadays actually your homework score is decreasing. So everybody can understand that situation. So it is an indication of your misunderstanding or so less achievement in this course. So I think that is a warning sign for all of us. So please have certain attention on this course. And yes, especially he reported that actually when we go to homework 20, and especially it's problem 3, almost no student has successfully solved this problem. So this is nothing but try to get the maximum gain out of certain amplifier. So here we are now talking about certain situation. Here we have a certain bias voltage, of course, and of course here we have a certain bias voltage. Gate voltage, DC by gate voltage, and DC drain voltage. Those voltages are already set by the designer, and if we insert a certain small signal input in this gate terminal and we try to observe this output voltage fluctuation, and we will try to get the relationship between this output voltage. Of course this is time dependent one, and another one, this is input one, that is also time dependent one. Of course, since we have two time dependent quantities, actually just taking the ratio, that does not make any sense, because for example sometimes V in can have its maximum value and its minimum value. However, sometimes it can have also number zero. Then how can we define the simple ratio of V out and V in? That is not possible. Instead of that, we try to make a certain relation between their amplitude. So of course when we take an amplitude, then the ratio of those amplitudes is given by voltage gain. But voltage gain, sometimes we call it as a certain negative value. It simply means that when you increase V in by a factor of, for example, 1 millivolt positive, then let's say that your V, so voltage gain is given by -10. It simply means that if you increase your input voltage by 1 millivolt, then you will observe the decrease of your drain voltage by 10 millivolt. So the ratio is just -10, and the negative sign appearing in this voltage gain simply means that when you increase the input, then you will have the decrease the output. So that is one thing. And let's come back once again, homework 20, problem number 3, which is not very successfully solved by all of you, most of you. So in this case, my question was, I have no predefined condition for our VGDC. So you can select VGDC, anything you want to have. So just changing your value, this value, then you will have different bias conditions. Of course, in this case, you have freedom to select VGDC. Once you select this one, since every quantity is inside this amplifier topology is given, so your VD DC is automatically given. So there is only one single independent variable, and this is just a dependent variable. Once you select, say that, oh, I will use 1.0 as a DC bias condition, then you will have a certain determined VD DC. So once you have that one, you can make a certain voltage gain out of it. the question was, it's up to you. You can have freedom to select VGDC and try to find out the voltage where your voltage gain is maximized. Then how can you do that? In order to achieve this goal, first of all, you have to make a certain assumption. Which assumption? Assumption about your operational reason. Means that here we have a certain VGDC, then automatically that DC drain voltage is given. Then depending on their relative magnitude, means that, for example, we can make the difference or relative magnitude between these two quantities, gate overdrive voltage and drain bias voltage. What happens if we have this condition? Then what is the assumed operational reason? That is the triode reason. So, and in other way, if we have this condition, if the equality is inverted, so drain bias voltage is even higher than applied gate overdrive voltage, then what is it? In this case, we can assume that this transistor is operated in the saturation mode. So first of all, you have to say that we can have two possibilities. One that is in the triode mode region, and one is in the saturation mode region. Once you accept those two cases, then I hope that you can calculate the gain out of it, because depending on the situation, you have a well-defined ID versus ID versus VGS and VDS is well defined once you have the operational reason predefined. So based upon that one, you can calculate your gain for those operational reasons. And please try to select the maximum one. That is just a general comment. And one thing we can say further, more intuitively, is like this. So first of all, however, I think that understanding this general discussion is important. And after that, once you understand this one, then later, from now on, let's think about the specific behavior. So this is the input and output voltage space, and I will try to once again draw the voltage transfer curve. So how does it look like? So below threshold voltage, the output voltage is just equal to VDD, because our M MOSFET is now turned off and no current conduction, so our VDD is just copied into our drain node. So after that, we have a certain almost parabolic behavior here. Then my question is, what is it? What is the operational reason of this parabolic curve? Certainly you can say that this is the transistor located in its saturation mode. So please try to make a comparison between the slope just nearby this knee point and this part. Where do you have a larger gain in terms of its absolute value? Maybe the gain in this part would be just like this, and maybe the gain at this point is like this. You can easily understand this is just the inverted parabolic curve. So if you go further from this center point located here, then you will have a more steeper line for your normal line. So it is certain that as much as your device is operated in the saturation mode, then it would be better to have a larger gate overdrive voltage. That is general trend. However, there is one limitation. Your curve does not behave like this. No, this is not the case. Once you increase your gate voltage, gate overdrive voltage sufficiently, then you will have more current flowing through the resistor, and you will have a larger voltage drop across your resistor. drain resistor. So what will happen? Your one bias point is fixed to VDD, and you have a larger voltage drop. So you will have smaller and smaller drain voltage. So once your device is now entered into what? Entered into the triode region. For example, let's say that this is the point. Then what will happen? Suddenly, now your slope is decreasing because triode mode region. So you have a lower velocity. So you have this curve. So intuitively, you can understand the point where you have maximum value for your voltage gain would be here. So why? Because in this part you have ever increasing voltage voltage gain, and this is the end of your saturation mode. So after that your gain will be decreasing, so that will be the point. However, there is also another thing. So what would be then best point for you to set up your operational voltage for your input voltage? Maybe once you accept this, all of this condition, you may say that, okay, then maybe this knee point would be the right position for our selecting this guy. However, please note that this is just a border between your saturation region and triode mode region. And please note that if you insert something, some perturbation or input signal into your signal, then your device will just cross over between the saturation mode and triode mode. So that is not certainly a good situation. So of course you have to certain margin for your operation, and actually this point, this kind of voltage transfer curve was simply obtained from our assumption of constantness of mobility. As I told you before, this mobility itself is also a function of your gate source voltage. So your curve, the realistic curve, really shows certain deviation from this one. So calculated from constant mobility one. So in reality, the point you have to find the best result is not determined by this border point between saturation and triode, but the point where you have a certain other quantity, other condition. Okay, so I think that this is just a description about homework number 20. So actual calculation is up to you, but please do it again if you have not successfully done your homework number 20, problem 3. So because that it will be important for your understanding on this situation. So anyway, it simply means that in many cases your transistor in the amplifier really working in the saturation mode. So for while, just let's assume that your device is operated in the saturation mode. Why? Once again, it is because in this case you have a larger voltage gain. So amplifier has many different requirements for its operation. However, the simple most important one would be just gain. So if it does not amplify signal, it is not useful. For example, let's say that the voltage gain is just 1, or voltage gain is -1. Do you like it or don't like it? You just say something and it is magnified and it has the same magnitude. Oh, of course it is magnified with amplitude or voltage gain of 1 or -1, but maybe you don't feel that that is actually actual amplification. Instead of that, think about this one. For example, you have 1000 and -1000. So in this case, that is real amplification. Your millimeter, so your microvolt level signal is now amplified to your 1 millimeter, your 1 microvolt signal is now amplified to your 1 millivolt signal. That is the real amplification. So in order to have maximize the voltage gain, so usually we operate our device. The device means that here transistor in saturation region. Okay. Do you have any question about the explanation up to now? So please feel free to give me any feedback. So then why don't you go to the review of our previous lecture, lecture 21. So we are now talking about the same structure once again, but however, what we have done is, yes, we wanted to have a certain amplification. Let's say that this is amplifier, and in order to operate this amplifier, we have to provide two signals, two voltages component. Like, first of all, we have to provide the DC gate voltage. Also, we have to provide our input signal. This is the small signal one, and they should be applied to our input terminal as simultaneously. So how can we achieve this one? So we have assumed that here we have a certain point where we have input voltage that really contains the information. Information is located here, and of course it can have its own DC voltage. That is not very desirable to us. We just wanted to take only the signal. Signal means that AC component. Then how can we construct the input part to just take this valuable signal out of this situation? So simply means that the answer was amazingly simple. We can introduce certain capacitor. Then this capacitor can be used as a blocking layer for your DC voltage. So if we have a certain DC voltage here, then that cannot be transferred to this node, because so capacitor is really infinitely blocking this signal, and only when we consider AC signal shown here as V in, that can be just copied into this input node. Of course, there is certain condition. For example, if we introduce extremely small capacitance, then what will happen? Then it does not make any role for this one. Your voltage, small signal voltage, cannot be copied into your input terminal. Once you have sufficiently large, sufficiently large capacitor, then your voltage can be copied into this input terminal. Then it is simply because the impedance of your capacitor was given by just 1 over j omega c at a frequency of f, or angular frequency of omega. So if you have a sufficiently large capacitor, then your impedance originates from the capacitor, goes down, so you will have a very good electrical connection between your signal node and input node here. This and that can be connected through very low impedance line. Okay, so do you have any question? So that was the simple rule we have studied in our previous lecture. So now, simply speaking, the situation is like this. We will have certain DC biasing circuit. So DC is simply DC voltage here is simply set by DC biasing circuit here. For example, the simplest one would be like this. For example, you have VDD and you have ground here, and by using certain ratio between two serially connected resistors, you can select your DC voltage. In DC scene, how about this capacitor? If we are looking at DC, this capacitor does not play any role, because you can say that the two nodes connected by a capacitor can be considered as just disconnected ones, because once again capacitor provide us infinite impedance for this case. Okay, do you have any question? I think that although we have spent quite a long time about our in our previous lecture, but simply speaking, I just told you that how can we implement this biasing circuit, how can we provide DC voltage, at the same time how can we supply the small signal input into our input terminal. So once you understand this one, then yes, you have plenty of resources. However, in many cases you will find this one. For example, if you are looking at certain, can we say, certain exercise problem in textbooks, then you will find this one. Yes, you have full information about your N MOSFET. Here you have a resistor and VDD, and simply it says that this problem says that okay, VG equal to something, and yes, that's it. For example, it says that gate bias is 1 volt. Of course, you have full knowledge about this transistor, and resistance is also given. For example, it can be 1 kilo ohm or blah blah blah, and you have full information about W, L, mobility, or oxide capacitance. You have, of course, most important thing is also threshold voltage of this transistor. And in this case, usually the problem, exercise problem, asks you, please try to calculate your voltage gain for this system. But simply speaking, although that is shown as this simple diagram, please note that it really assumes that in order to really achieve this circuit, then you have to provide something like this. Here, DC bias voltage to achieve this one, for example. Yes, you have to one DC biasing circuit, and also provide a certain capacitor to blocking your DC input voltage. Okay, so that is understood. So are you with me? So although you have just the serially connected transistor and resistor, it just assume the existence of a biasing circuit and capacitance, blocking capacitance as granted. So that is always understood by you and me and all other engineers. Okay. Then now the goal is, once you accept this situation, then our today's lecture, lecture 22, goes about what is the gain obtained from this condition. That is our goal. Of course, you may say that, okay, we have already done in our homework 20, problem number 3, or 1, 2. We can now calculate at any time the voltage gain. Yes, you are right. You can always calculate the voltage gain by doing this job. For example, yes, you have a certain amplifier structure, then you can find the VD and VG and draw something and always take the derivative, then you will get the voltage gain, the slope of your voltage transfer curve will be the voltage gain. So are you with me? So once you have this curve, then it's okay. You can always get the solution. But point is, so in order to calculate the voltage gain quickly and intuitively, the general rule is first to calculate the full voltage transfer curve and take the derivative. Then you will get the answer. In principle, that sounds great. However, that will take a certain time for you. So instead of that, people wanted to develop a quicker way and more intuitive and more inspiring way to calculate the voltage gain. So today we will talk about how can we model this system more intuitively and get the result more quickly. Okay, so before starting today's lecture, so I want to once again remind you that in principle calculating of voltage gain is so straightforward. Once you have full knowledge about its input and output characteristics, everything will be quite perfect. So just taking the normal line, yes, that's it. However, a simpler way is introduced here, and I think that is more important than just blindly solve the voltage transfer curve in this case. Okay, so once again, if you have any question, then please interrupt me. So now think about this guy, this system of our interest. Yes, we assume that we have a full knowledge about parameters. There is no unknown parameters and everything is just given. So now our only remaining question is, now we have introduced V in here. For example, V in can be, for example, let's say that I have added 1 microvolt. Then my question is, okay, then what will be the small deviation in this drain node? For example, if this one is given by 1 millivolt, minus 1 millivolt, if I increase input voltage just to 1 microvolt and assume that drain voltage is decreased with 1 millivolt, then we will say that here we have minus 1 millivolt and 1 microvolt. So we will have a ratio of minus 10 to the 3. That will be the voltage gain of this system. So let's say that in this case V is equal to 1 volt, and let's assume, just assume that VD, its DC component is happen to be, for example, let's say 0.5 volt. Then I wanted to ask you, somebody calculated this one. If we calculate the voltage gain like 1.1 plus 10 to the minus 6 divided by 0.5 plus 10 to the minus 3, what happens? Do you feel that this is a reasonable way to define or calculate the voltage gain? So here I just added our DC component, DC input voltage and DC output voltage, and take the overall ratio between the entire input voltage and entire output voltage. You know that that will be just half, 1/2, and this is nothing related with its actual application. 0.5, who cares? This is not the case. Whether input voltage is 1 or input DC voltage is 1 and DC output voltage is 0.5 volt, that does not make any sense in our application. What we wanted to know is just ratio between this AC component and AC component. That's the important observation. So please note that once we are talking about the amplifier, then we have to consider certain system in our mind, like just considering the input and output relationship between only AC component. So let me just emphasize this one, this important rule once again. So in general, here we have amplifier, and in this amplifier we usually insert VG DC plus V in. Yes, that is the real situation. And as an action of this amplifier, we will have DC plus V out. That is the real situation. The real situation means that the circuit schematic shown here is working as an amplifier. However, when we try to get certain knowledge about voltage gain, this view, although quite general, is not that much important. So just taking the ratio between this entire output and this entire input, no, we have to avoid it. Instead of that, please try to draw more suitable description about this one. How do you calculate or draw certain diagram? Here we have amplifier circuit, and in this system, in this diagram, we just consider input signal, AC signal only, and calculate the output signal only. So of course I wanted to ask you, is there any real system or real circuit which just takes AC and just generate AC? As I told you before, in order to operate this amplifier, we have to spend our DC power. Otherwise, this amplifier does not work. For example, say that I just introduce 0 voltage here. 0 voltage as an input gate bias. Then what will happen? Of course, I can introduce small signal. However, your transistor is completely turned off and no current will flow at all. Yes, so in this case you will have just one, or you will have just a VDD, and your output voltage will be just 0, although you have a non-zero value here. So now you can understand. In order to operate your system, your circuit as an amplifier, first of all you have to spend your DC. That is your cost. You have to spend the DC power. With the cost of DC power, you get the amplification shown here. So although there is no system like just to live with its AC component and its AC component, but in our mind we just construct this artificial system. Say that its input just to consider AC and output is AC. Okay, so we will try to now consider this system. What is the relationship between input and output? So now let's come back to this guy. If we take this rule, and when you have a look at this IB so this circuit schematic, now it becomes quite clear. So by the way, if you cannot understand the concept shown here, the boxed here, highlighted here, then please let me know. So I will explain it again and again. And Okay, I will start a new one here. So now you understand the situation. Simply I will give the rule here. Now we have a resistor, and here we have VDD. Yes, it is a DC voltage. So if we try to construct a system considering only AC one, then our natural question is, what is the AC voltage related with this node? So can you find it? Yes, the answer is, although this is VDD, but we have no AC component. So in AC wise, in AC term, we have to consider it as just ground. Okay, so that is one thing. For example, think about this one. Here we have a transistor, and here we have a VGDC plus Vin. Then let's think about this guy. Then what is the voltage in AC scene? Here we have DC input component and small signal input. However, if we consider only AC scene, then we have to say, yes, quite simply, V out. You know it quite well. Also VDDC plus we will have V out. What will be the remaining term for AC consideration? Obviously, you have to consider this guy only. Yes, there exists the DC component, but that does not play any role in our AC consideration. Of course, here we have ground. Oh, ground has both of 0 voltage and 0 AC voltage. Still, it will work as just ground. So if we just follow this simple rule, okay, simply speaking, DC voltage is neglected, then how can we draw this system? Now we will have certain model related with our transistor. Yes, here we have a transistor, and it is connected to our AC ground, and here we have only input signal, and here we have still resistor. Okay, resistor is still resistor, and output is V out. And finally, the one thing usually students from my experience, students have some difficulties to understand is this guy should be regarded as connected to the ground. So although I have written here, drawn here as a ground, it does not mean that that is actually ground. This simply means that this is corresponding to AC ground. No AC signal is allowed for that point. That is the implication. So here, so although it is just written like a circuit schematic, however, it is different from the one shown here. The upper one is the realistic one. It can consider both of time dependent signal and time independent signal, DC signal. But here we have made certain artificial system only in our brain, and it takes only AC component here. So please have a look at this guy. Okay. Do you have any question? So once you have any kind of the real circuit diagram, circuit schematic, then just eliminating your DC component, then you can easily construct this AC circuit for your system. That's not that bad. But point is, instead of drawing the MOSFET symbol here, I intentionally introduce a certain box. Oh, there is something here. There is something. Why? The reason is so simple. why did I just draw resistor as a resistor? Resistor is a linear circuit element, so its component can be just copied, used in as usual in this AC diagram. However, in the case of our transistor, you know that transistor is a non-linear circuit, circuit element. So just writing this nonlinear circuit component here is not very useful to us. So you know that the magnitude of your V in and magnitude of V out are assumed to be quite small, so like just microvolt or millivolt scale. So you can always take the derivative, so linearization of this nonlinear behavior is allowed. For example, let's say think about this one. Here we have ID, which is given by VGS and VDS. This is a general nonlinear relationship. However, what we want to get is like this. Of course, if we have small change in our input voltage and small change in our output voltage, then we will have also small change in our drain current. That is the thing we wanted to get. So simply speaking, we wanted to make certain linearized system between our voltages and currents. That should be shown here as a black box here. Here means that this guy. So our natural question is, how can we draw or how can we represent this transistor in the linearized sense? That is my question. And fortunately, we have done it already. So do you remember? So let me just try. So since we have only two terminals as an input and output, so we can define this guy. Oh, sorry, where is it? We can define ID and IG. Also, we can define the excitation voltage, two excitation voltage like gate source voltage, and yes, and yes, yes. Simply speaking, we have two non-trivial, non-referenced terminals and also two terminal currents, gate voltage and drain voltage. That is quite general, so think about this one. Here we have grounded port, terminal, which is called as source. However, source is always grounded. And here we have input, gate, and output, drain. So we can define the voltage VG and voltage, oh sorry, here, voltage VD, and also define current IG and current ID. So simply speaking, we can think about certain relationship like this. Yes, we have VG and VD. That determines IG and ID. That is, there can exist non-linear relationship between these four components. So, however, fortunately, we have already studied that. So, in our low frequency approximation, what is the assumption? So, can you say IG is assumed to be almost zero? Or, of course, at zero frequency, that is still true. And even when we have a low frequency limit, then we can neglect the gate current. So because the operation frequency is low. And how about drain current? In the case of drain current, we have a really good approximation. So depending on its gate voltage and drain voltage, maybe you remember those expressions. Maybe we have studied three different expressions. So now you have a nonlinear relationship between this one. For example, yes, this guy is a nonlinear function of Vg at the same time Vd. But point is not this relation, not this general relation. What you wanted to get from now on is simply, instead of this full Vg, Vd, Id, Ig, so you wanted to have small deviation of your gate voltage. Yes, this is corresponding to your Vin, and small deviation in your drain voltage. Yes, this is corresponding to your what? Your output voltage. And you will get also change of your drain or gate current, but it is assumed to be 0. Yes, and you will have small deviation in your drain current. And since they are assumed to be small, so now instead of this non-linear relationship between these four quantities, instead of that, we can now try to build a matrix. Matrix means that simply representing the linear relationship between quantities. Now we can introduce four different components for describing our our small signal quantities. So usually, instead of this V matrix, V vector is given by something like this. This type of point of view is corresponding to impedance. But instead of that, why don't you just try to do the opposite way, like this? I equal to voltage multiplied by something. So what is the name of this matrix? We have already studied it. That was, yes, y parameter. So we have studied it in our previous second last lecture, or third last lecture. So simply speaking, we can say delta Ig and delta Id, and that is mediated by our y parameter, and here we have voltage vector corresponding to delta Vg and delta Vd. Then how can we fill out those four components? So you can easily understand, in order to make this relation reasonable, then what you have to introduce is like this. For example, we have to introduce round Ig over round Vg is required as a 1,1 entry in this field. Okay, so are you with me? So if you cannot see it clearly, then let me just magnify it here. So can you see it clearly? So of course, in this part, we have to introduce a round Ig over round Vd as a 1,2 component. So that is quite easy to expand it. Once again, Vg, and finally you will have Vd. Okay. So do you have any question? So in the last couple of minutes, I have explained the concept of y parameter, and the y parameter can be defined in this way. When we just evaluated this matrix vector multiplication, now we have a quite clear understanding. Delta Ig is given by this partial derivative multiplied by delta G. Here we have delta Vg and partial derivative with respect to Vg, so we will have delta over Ig. And also we have a product between them, and here we have Vd. They can also give us response of gate voltage. So everybody can understand this one. So if you have any question, then please let me know. And remember that even these components are defined in our previous lecture. So what was it? So first of all, since we have assumed that gate current is anyhow vanishing, so simply speaking, we just say this is 0 and this is 0 at low frequency. I wanted to say that this is valid at low frequency. And now we only have two components. Simply speaking, response of your drain current with respect to gate. What will happen if you change gate voltage? Then to your drain current. That is one quantity. And another quantity is round ID over round partial derivative with respect to VD. Then what will happen if you change your drain voltage further, and what will happen to your drain current? And as you can see, this guy has its own name. What was it? It was defined as Transconductance. So do you remember? So it has its own symbol called G sub M, GM. Yes, so we have GM, transconductance. As I told you before, transconductance shows a certain peak point. So the point of gate bias voltage where transconductance shows the peak voltage, peak value is the most preferred operational voltage for analog engineer. So you remember this one. And how about this one? So this is round ID over round VD, and that was defined as inverse of our output resistance. So I'm afraid that actually you have already forgotten this already determined quantities. GM and R out were defined in our previous lecture, but anyway, their definition is given by this way. Then let's come back. Yes, now simply speaking, now we treat in this way. Yeah. So we are now talking about the black box for transistor. Yes, so now we have, yes, now we have something like this. In this black box, we have VG, and here we have VD, small signal one, delta VG, delta VD, and also we have small change of gate current and small change of drain current. But repeatedly at low frequency, we have assumed that this one does not appear at all. So now our goal was like this. Yes, this ID now can be written as what? Written as like this. GM multiplied by our delta VG plus what? Delta VD divided by which quantity? So in this case we have R out, because our Y parameter, it's a 2, 2 component, was defined as 1 over R out, so we will have this form. So simply speaking, now think about this guy taken from this expression shown here. Now we wanted to draw certain equivalent circuit for this drain current. So let me just do it. Yes, here we have drain, and it has two components, two current components. One component is proportional to delta VG, and another component proportional to delta VD. So since we have two components, why don't we just draw two components separately? Because you know this is current, So parallel branches can contribute to addition of our current. Okay, so can you understand here? So simply speaking, we are now talking about drain, and here we have a grounded source. And we have here the component corresponding to Gm delta Vg, and here we have the term related with delta Vd divided by R out. So are you with me? I'm just drawing this simple relation taken from our Y parameter into circuit diagram. So here this branch is corresponding to Gm delta Vg, and another branch is corresponding to delta Vd divided by R out. Once you accept this kind of description, then now you can immediately, almost immediately understand the box shown here. The box shown here should be written as just a resistor whose resistance is R out. So are you okay? So we have a certain current. Current is given by delta Vd divided by R out, and their voltage difference is once again delta Vd, because this is AC grounded and this is delta Vd. So simply speaking, this component can be just considered as a normal resistor. Then maybe you are just tempted to draw even this box like this. So let me just make a long interpretation. Okay, inspired by this resistor, I just draw here once again a resistor. Wow, and its value is given by 1 over Gm. If I draw in this way, this is completely wrong. Why I am wrong? So you know, here we have resistance corresponding to 1 over Gm, and in order to, if this is really a resistor, then the component should be written as just Gm multiplied by delta Vd, not delta Vg. So are you with me? This point is important. If I use the resistor symbol, then resistor just depends on the voltage across itself. However, unfortunately, the voltage makes impact for this component is not the voltage across this component, this black box. Instead of that, it is controlled by what? It is controlled by other voltage difference. Here we have Gm, and that part is controlled by our voltage difference between source and gate. Here we have delta Vg. Delta Vgs. Okay, anyway, here we have this condition. So then question is, how can you write down this component? It is now become obvious that here we cannot use the resistor symbol. Once you introduce resistor symbol, then current should depend on this difference. However, unfortunately, this guy just depends on voltage difference between not these two nodes, but these two nodes. That's the problem. So instead of this resistor-like expression, instead of that, we just simply introduce, okay, I will use blue color for your interest. instead of that resistor, we'll just introduce a voltage source and say that its amplitude or its magnitude is given by just Gm multiplied by delta Vg. Delta Vg. That is the reason why we have two different symbols. Oh, of course, if we can just write them as resistors, then everybody will be happy. However, since the physical nature of this component is remote control of drain current by your gate voltage, I think that this is at the heart of the operation of a transistor. What is the most important thing of transistor operation is the drain current is not only determined by drain voltage itself. Drain current is remotely controlled by other terminal called gate. So that's the reason why we call it as transistor. Also we call this GM as transconductance. Trans means that terminal is transferred. Voltage at gate terminal is transferred to the current in the drain terminal. So therefore, since their physical meaning are different, we have to unfortunately use these two different symbols. And usually this kind of thing, the current source, however, its magnitude is not an independent value, but its magnitude is given by just a function of another voltage. So that is usually called as voltage controlled current source. This is nothing but, usually when we say voltage source or current source, usually normal one is just 1 milliamp or 1 microamp. So its magnitude is given. However, instead of that, this so-called voltage controlled current source, its value is simply given by a function of different voltages. That's it. So now let me finalize today's lecture. So now instead of this black box wise description, now we have to draw our circuit in this way. Now we have V in, yes, now we have V in, and now I will draw our equivalent circuit in this area. Okay. Okay, it's stopped once again. Come on. Okay, I can try once again. So now, as a result of our all-over discussion, now we will have this final form. So when we draw the AC equivalent circuit of our amplifier here, then now we have V out, and here we have V in, and source is grounded once again. And now I will fill this part corresponding to our transistor. Then how can we draw it? Here we have voltage controlled current source, and its magnitude is simply dependent on the voltage difference between gate and source. So this is simply V in here, and here we have GM V in, and after that we have parallel line, parallel branch, so which is connected between drain and source once again. However, its value, its resistance value is simply given by V out, and that is connected to this node. Do you have any questions? So what we have done in this case is just I introduced the equivalent model for our transistor. Simply speaking, from the definition of Y parameters, we can easily build this equivalent circuit. Okay, so now your drain current can be decomposed into two parts. One part is corresponding to delta VG, and one part is corresponding to delta VD. And these two terms are separated into two branches, and that is shown here. So I think that if you have listened up to now, then maybe it's not that difficult to understand this guy. Then what is the beauty of this approach? So please come back to the starting point of our lecture 22. As I told you before, the calculation of gain is so straightforward once you can full information about voltage transfer curve. If you can draw this relation V in and V out, then everything will be just immediately given to you. So just taking the derivative, you will get the voltage gain. However, instead of that quite straightforward way, we just make a shortcut to get the voltage gain. So once we have this AC-wise system, then since everything is just written as a current source and voltage source, the things becomes amazingly simple. So let me just follow this one. So let me just follow. How can we simplify this diagram? So now I assume that all of you are understanding the existence of this equivalent circuit. Then let me just draw it in a simplified manner. Yes, here we have V in, no change, and here we have V in. Yes, there is no change, and here we have ground and no change, and here we have also voltage controlled current source GM V in, no change at all. However, when you consider this node, we can find two connected resistors. So why don't you just draw them? I will just draw one resistor and another resistor. One resistor is R out here. Another resistor is R here. So in order to make it clearly different from other one, let's just call it as a drain resistance RD. Let's call it as here also RD. Then my question is, yes, one terminal is connected to our V out node. Then how about the other node? Other terminal is connected to what? In the case of R out, it is connected to AC ground. So are you with me? Yes. And please think about RD. RD. What is the connected node? Still, even in this case, it is connected to ground. So are you with me? So the simple point is, of course, in reality, if we consider general schematic, of course RD is connected to VDD. This is not at all the ground. However, if we consider only AC component, then VDD also can be considered as an AC ground. That's the reason why R out and RD can be regarded as two resistors parallelly connecting the output node and AC ground. Okay, then this is corresponding to your V out. So if you accept this one, then the remaining procedure is amazingly simple. Since they are parallelly connected, so we can define the equivalent resistance. So how can I write down R out parallel RD? We can define this quantity. Of course, this R out parallel RD can be explicitly written as R out multiplied by RD divided by sum of them. So that is quite easy. So now you have this form. Finally, really finally, think about the expression about V out. How can you calculate V out? What is V out? In this case, we have to apply the KCL for this out node. Then how can we how can you write down the KCL? KCL simply means that sum of branch current should vanish. So please try to write down your branch current. So I would like this write out in this way. One branch current and another branch current, their sum should be 0. One branch current is given by GM V in. Another branch current is given by V out divided by R out parallel RD. So are you with me? So this is just a sum of two branch current. So from this simple KCL applied to our output node, we can finally write down in this way. V out is given by minus times GM R out parallel RD and V in. So are you with me? This is just simply, I just put it here and multiply this equivalent resistance to left hand side and both right hand side, then we will get this form. So finally we will have voltage gain, which is given by the ratio between V out and V in, is given as minus GM and parallel resistance between R out and RD. Okay, so you can find that if you wanted to maximize the absolute value of your voltage gain, what is your first choice? Of course, if you wanted to maximize the absolute value of your voltage gain, then you have to maximize your transconductance. Good. Maximizing transconductance would be the best way to get larger and larger voltage gain. However, we have another component we have not thought here yet. This is R out parallel RD. So the parallel resistance is given by what? So if you have two parallelly connected lines, resistors, and one is large and one is small, then who decide this overall resistance? Which one determines the overall resistance? The smaller one determines the overall resistance. So think about two cases. Oh, okay, the time is up, so let's wrap up here, and we will continue this discussion in this Wednesday. Okay, thank you. Bye.